All right, I guess we better check to see what happened on Facebook compared to the other day. The other day we celebrated pi minus 0.03 day. Today we'll try to celebrate pi minus 0.01 if I can keep track of the time. But what happened on Facebook? I did the countdown. I'm not going to do a countdown today for this. And I did get some likes and some comments. And I found out, moreover, I found out who sent it to me. I was thinking it was a student that sent it to me because I had some students say, hey, Dr. Kenny, you want to buy a shirt in the fall? So I was thinking they sent me a shirt. But no, it was my mom. My mom said, guess who sent it? Didn't you see that? And so yeah, it was from her. She sent me the Pi Day shirt without letting me know. She's actually in Israel right now. I'm over there. Anyway, that solves the mystery. We will try to go to stop at 9:26:53 again, if I happen to miss it. But we better do some differential equations first. It is the last day before spring break here at Bethel, so we will try to cut this class a little bit short to give you a little treat. So I'm going to try to aim for a 40-minute class. We'll see if I'm successful in that. I think it would be good to start off today to focus on the main content of the completion homework. That's due after spring break, actually not the day after, though we will meet. Okay, let's see. That would be today is the 13th, 23rd, I think is a Monday. That sound right? 23rd is a Monday. We do meet that day, but no homework due that day. The homework is going to be due the next morning by 9 o'clock at my office. Okay, to give you a little extra cushion. But the homework after that will be due Wednesday, so, and that's the usual time at 3 o'clock. I think it would be good to do chapter 3 stuff first today to make sure we get that in, and then if we have time, we'll come back to the SIR model for an epidemic and possibly the Lorentz attractor again. All right, I think what I'm going to do is I'm going to illustrate the idea about the linearity principle in the context of an example. I've got 2 examples here, in fact. 2 matrices. Focus on the first matrix here. A equals 1, 3, 2, 2. First thing you should realize in this type of problem, what I'm referring to is a differential equation in matrix vector form that looks like this. And that's going to correspond to a system of first order scalar equations. Capital Y is a vector whose components are little x and little y. And so d capital Y dt corresponds to a vector whose components are dx dt and d little y dt. A times y is this matrix times this vector. And by what I said the other day, what does that mean? It means take the first row of the matrix, 1 and 3, and take the so-called dot product of that row with this column vector, which means multiply the first number there times the first number there, add the product of the second number with the second number. So in this case, that gives 1 times x plus 3 times y. X plus 3y is the right-hand side of the dx dt equation. Now I go to the second row. Take the first entry, it's a 2 multiplied times the first entry of capital Y, 2 times x, plus the second entry times the second entry, 2x plus 2y is what you get with dot product. That's just the way matrix multiplication is defined because it makes a lot of sense, for example, for relating these two things. There's one reason we define matrix multiplication times a vector in that way. So you should realize that these two things mean the same thing. That's the first thing to realize. All right, let's go to the computer. This is a coupled system. Okay, it's not decoupled at all. It's not fully decoupled. It's not partially decoupled. It's coupled. The right-hand sides have both x and y in them in both equations. X and y are tied together. They are coupled together. So we, as of the moment, don't have any way to figure out what solutions to this are. Let's go ahead and enter the matrix here, and then let's take a look at the VectorPlot and StreamPlot. vector field and the stream plot of the solution curves. So I'm going to show a vector plot. Well, I could type in f and g. I actually don't have to here. I will eventually use them. This is what I'm calling little f of xy, and this is little g of xy. I'm not going to type them in immediately. I will type them in when I put the nullclines in. Actually, I may not bother giving them names on Mathematica, but we will get the nullclines into the picture too. In fact, maybe that's the first thing we should do. Let's make a contour plot of the nullclines and see if we, based on what we see with the contour plot, if we can kind of predict what's going to happen. It's our first practice in using nullclines. So I'm going to do a contour plot of, first of all, the x nullcline. That's where, remember, dx dt is 0. It's a curve in general, where your velocity vector for your solution curve, in other words, the vector field itself, has no x component. The x component is 0. It points straight up or straight down along an x nullcline. Along the y nullcline, it points straight right or straight left. So I set the right-hand side of the f of xy of the dx dt equation equal to 0. X plus 3y equals 0. I'm going to see the x nullcline. There it is. See, I always forget, can you do two things in here at once? I think you can. Can I get the y nullcline in there too? Let me try that. It's 2x plus 2y equals 0. Yep, can get them at the same time. Get rid of the frame, add some axes. The axes would be labeled with x and y. I forgot which one was the x nullcline. We can figure it out. The x nullcline is that equation. If you solve that for y as a function of x, you'll get y equals negative 1/3 x. Right, subtract x and divide by 3. You need a line with the slope of negative 1/3. This is the x nullcline. This one's the y nullcline. So the vector field is going to be vertical along this line and horizontal along this line. How do you figure out which direction though? Up, down, left, right? You'd have to look at the sign of the other right-hand side. For example, along this blue line, which is the x nullcline, where the vector field is vertical, to figure out whether the vectors point up or down, you'd have to plug points on that line into the dy dt right-hand side. I might close the door a little bit more. Thanks. The dy dt right-hand side is that expression. When I'm over here, for example, at the point negative 3, positive 1, x is negative 3, y is positive 1. If I plug in x equals negative 3 there, I get negative 6. Y is positive 1, that gives me 2. Negative 6 plus 2 is negative 4. I get a negative quantity. That means dy dt is decreasing, or dy dt is negative, so y is decreasing. So the vector field's got to be pointing straight down there. Over here on the other side, for example, when x is 3 and y is negative 1, then that becomes positive, so the vector field is going to be pointing straight up over there. So whatever it looks like, it's pointing down there, up here. Well, how about here? For example, when x is negative 2, y is positive 2, you've got to look at that equation. That's the right-hand side for the dx dt equation. Plug in negative 2 for x, you get negative 2 there. Plug in positive 2 for y, you get 3 times 2 is 6. You're going to get a positive quantity here. dx dt is positive right here. You're going to be pointing to the right. I bet it's pointing to the left down there, and you can check it. It will be. You could try to draw in some solution curves based on that. And it seems to be the case based on the fact that probably like right in here, you're going to be moving to the northeast. Is my guess there. Let's see, here and here. I think down here, you're going to be moving to the southwest as time increases. And I think in here and here, probably you're going to be moving inward. All right, let's go ahead and use VectorPlot and StreamPlot to see if that really happens here. I don't have to type in the right-hand side functions here. Since I've got the matrix in here, I can just do this. Multiply the matrix times the vector xy. I have to type it into Mathematica as a list, but you're imagining if I handle the column vector, the dot does the matrix multiplication there. That's the way I can represent the vector field if I have the matrix A in there. Let's worry about making this look nicer later. There we go, just like I predicted. Let's add the nullclines into the picture now. I'll give this plot a name. I'll call it nullclines. Put it in here with the show. Let's see, I should probably put it underneath the other plot, so I'll put it first here. Exactly what I said. The vector field's vertical along this one, so your solution curves cross with a vertical tangent, and they are going down. Here they're going up. Here they cross with a horizontal tangent, going to the right here and to the left here. So you can, with enough practice and working with nullclines especially, you can predict what the solution curves are going to look like. Oh, let's make the vectors red. Vector style arrow red. Make the stream blue, a brighter blue at least. Stream style. I think I'll just leave the vectors as they are as far as their lengths go, so I won't do the vector scale option. You have an equilibrium point in this picture. Where?
0, 0.
Yeah, 0, 0, the origin. Why? Well, because any matrix times the 0 vector always gives you the 0 vector, which should make sense. Moreover, the 0 vector is the only vector such that when you multiply it, left multiplied by A, you get the 0 vector. How would you prove that? How would you prove the 0 vector is the only vector? 0 is the only equilibrium point here. How would you prove that algebraically? There's two ways you could do it.
Plug it into the system.
Well, if you plug in 0, 0 into the system, you'll confirm that 0, 0 does work, that it does give you an equilibrium point. What I'm asking for is, how do you know it's the only equilibrium point?
Shows that the columns of A are linearly independent.
Uh-huh, which is a linear algebra term, which can be done with a quick calculation, well, actually in two ways. Since these are just two vectors, you can look at these two columns, think of them as vectors. They're not multiples of each other. You can't multiply that vector by any scalar to get that vector, and vice versa. That's enough to show they're linearly independent, which will mean that the 0 vector is the only equilibrium point. There's another calculation the book talked about. Determinant, yeah, DEP. Take the determinant of the matrix and if it equals, or if it doesn't equal something, then you're guaranteed that the origin is the only equilibrium point for the system. What should I prove it does not equal? Does not equal 0. You multiply the entries on the main diagonal, 1 times 2, and subtract the product of the numbers in the off diagonal, 3 times 2. 2 minus 6 is -4. The important point about that is it's non-zero. And that is enough to prove that the origin is the only equilibrium point. I guess the third way you could do it is you could set these things equal to 0 and solve for x and y, and you'd only get one answer. The usual solving kind of technique, either by elimination or substitution. It effectively proves that if there is an answer, it will be the origin. But you can also prove that the origin definitely works in checking by plugging it back in. You should know this. Definitely comes up on exams. Know that if the determinant of the matrix is non-zero, that means the corresponding linear system only has the equilibrium point at the origin. That's its only equilibrium point. It will always be an equilibrium point for a linear system, and if the determinant is non-zero, it'll be the only equilibrium point. The determinant being non-zero means other things. It means the matrix A is called invertible, also said to be non-singular, another term used. If it does equal 0, that's sort of a rare thing, so it's called singular, but it's also non-invertible in that situation. Okay, so it gets a little confusing when you learn about the relationships between those. Non-singular means invertible, singular means not invertible, so it's confusing, the non-switches. That's terminology you should know. You really should put equilibrium points in your pictures with big dots to emphasize where they are because they're really important. Equilibrium points are really important, okay? So don't just leave your picture like this, add a big dot at the origin. You can do that either with graphics and point or with list plot. Here's basic syntax that will put a dot at the origin, though it's not real big. And I like to make it black. Point size is the sizing option you need to use. Oops. Let's see. Oh, that's outside of the list plot. My pasting didn't work. Ah. Style. If you put a 0.02 here, it does make it, well, a little bit bigger. Make it 0.03. I think what the 0.03 means is that the horizontal distance across this dot, the diameter of the dot, is 3% of the entire horizontal distance. We could test that. If I go to 0.5 here, would it be 50%? About right, I suppose.
Do one.
Do one? Okay.
Yeah, you're right.
Yep, looks good. So 0.03 usually is pretty big. I want you to notice something. I was going to use animation to visualize this, and maybe I will before I put it on Moodle. I was going to put this in manipulate, use graphics and arrow and locator to move around a dot, showing the output of the vector field at that point. Maybe I should. It's probably worth it. Okay, so I'm going to a little bit more practice with the locator, if nothing else. So I'm going to put an arrow in here. I'm going to use graphics and arrow, and let's make the arrow big, magenta maybe. Arrow. I need syntax that looks like this, where you put the starting point of the arrow of the vector at the point it's based at, which I'm going to call PT, and which I'm going to change with the locator command. It's going to be a point. It's going to be a list in Mathematica. And the end of the arrow, I don't want it to be A times PT, but instead, in fact, I want it to be a PT plus A times PT. That'll put the end of the arrow at the right point. Effectively, I have to first go to the starting point of the arrow before I add on the arrow itself. Okay. I'm going to put all this inside manipulate. And PT is going to be my animation parameter, but it's going to be a locator one. Question? It's time. Okay, countdown. What do we got here? Got to get to 53 if we don't round. 15, 14, 13, 12, 11. Get your time to get there. 9, 8, 7, 6, 5, 4, 3,
2, 1.
Yay!
Fireworks!
Pi minus 0.01 moment.
Where were the
Thanks for letting me
fireworks?
know. I wasn't really thinking about it at all.
Maybe cake?
No cake,
Oh, hi.
no pie. Missed pie yesterday.
It was just making sure that you're on top of things today.
Thanks. Here's the basic syntax for locator, creating a locator inside manipulate. Crosshairs that can be moved with your cursor to change the PT in this case. That'll change the arrow. Put the PT here and then put its starting point here. You can start it at the point 1, 1, for example. I've got too many curly braces here. Let's see. What is the problem? Get rid of that one. There you go. There's the output of the vector field at a given point. Let me add another vector in here. Let's make it green. Let's start it at the origin and go out to the point in question. And look at that. With the particular point that I picked, 1, 1, the green arrow and the magenta arrow are parallel. What is that going to mean? It's evidently going to mean, and it seems like they'll continue to be parallel even if I move this crosshairs up this direction along the line y equals x. It seems like they'd continue to be parallel, and they would be. And what that's going to mean is you're going to have a solution curve going straight, a straight line. A straight line solution. That's what it's called. If you look at the vector field and you see the symmetry, if I go to the point negative 1, 1, negative 1, negative 1, excuse me, looks like I have a straight line solution down there too. There's more. If I go to the point, well, it's hard to tell exactly where it is. Right around there. Not exactly. It looks like the output of the vector field, the magenta vector, is pointing straight toward the origin. Not exactly, but close enough. Parallel to the position vector of this point, the input, the green vector, but in the opposite direction. And again, by symmetry, we should expect something over on the other side too. Right about there. So you've got, in effect, 4 sets of straight line solutions. One solution that goes this way. By the way, that really corresponds to infinitely many solutions corresponding to infinitely many different initial conditions. But they're all related to each other. One going that way, one going this way, one going this way, one going that way. And it seems like the origin is some sort of saddle point because of it. I want to get out early. It's looking like we probably won't have time for the other stuff. That's okay. We'll come back to it, review it after spring break a bit. What I'm really after, if I'm going to algebraically solve for these lines, one of which does seem to be the line y equals x, is I really want to find a non-zero vector v, must be non-zero vector, and a scalar, a number, traditionally called lambda in this context, such that what happens? Think about it in terms of the vector field. The output of the vector field at the point v, which really means corresponding to the position vector for v, the green arrow, a times v is the output of the vector field. That should be parallel to v. It should be some scalar times v. Lambda is the scalar I'm using. Some lambda times v. Excuse me. We're looking for a non-zero vector v and a scalar lambda so that this is true. Lambda actually can be 0 in some examples, but v cannot be 0 when we're thinking about this. You're wondering, can that kind of equation be true? Can it be satisfied? Turns out, to give you the quick summary of what's going on here, not to spend too much time with this, it's beneficial to think of this thing as lambda times capital I times v, where capital I is called the 2 by 2 identity matrix. It's that matrix right there. And if you think about it, if you multiply that matrix times any vector, any two-dimensional vector, you get the vector back. It's got a name, it's called the 2 by 2 identity matrix. It acts like the number 1, because when you multiply 1 times any number, you get that number. Here, when you multiply this 2 by 2 matrix by any 2 by 1 vector, you get that vector back. So this identity matrix acts like the number 1. And so therefore, that's why I can write this, v equals I times v. That's a beneficial thing to do because I can now rewrite this equation, first of all, by subtracting lambda times I times v from both sides. To make it look like this, where the right-hand side would become the 0 vector. Then I can factor out a v, that's why I put the I in there, so that I have a matrix involving a, lambda, and capital I times the vector v. I can factor the v out here. I can write this in this form. Now this is just a matrix, a 2 by 2 matrix. We can figure out what it is. It does depend on lambda. This is an algebra equation involving a 2 by 2 matrix and an unknown 2 by 1 vector. This is still xy, if you like. This is 0, 0. In fact, because the right-hand side is the 0 vector, this is called this is not surprising, a homogeneous equation. It's not a homogeneous differential equation, it's a homogeneous algebra equation, matrix vector equation. And based on what I just said a few minutes ago about the original system having the origin at its only equilibrium point if and only if its determinant was 0, I erased it, it was up here. Well, I guess I calculated the determinant, saw it was non-zero, and then I verbally said to you that fact. That same fact can be brought to bear to say, well, this equation is only going to have v equals 0 as its only solution if the determinant of this is non-zero. Moreover, if the determinant of this is 0, there will be non-zero solutions for v to solve this equation, which is what I'm after. Non-zero. So, I really want to figure out what values of lambda will make the determinant of this equal to 0. If I can find those values of lambda, if they exist, then this matrix will be singular, non-invertible, its determinant will be 0, and this equation will have non-zero solutions for v, which is what I want. I'm trying to find those straight line solutions. I'm trying to find, I guess I didn't really emphasize that enough, I'm trying to figure out, I did say it, but I'll say it again. I'm trying to find out points, if you like, position vectors for points in the plane v, such that the output of the vector field, a times v, is a scalar multiple of the input, so that those vectors that I draw on the screen are parallel. Those are special solutions. That's going to help me find those straight line solutions. So because of this, I really find the determinant of a minus lambda I, and I set it equal to 0 in the hope that I can find some non-zero v's that will make that original equation that I circled over here true for some lambda. What is a minus lambda I? Well, here's a. What's lambda I? There's I. Should make intuitive sense that if you multiply that by lambda, a scalar, a number, then you're going to multiply every entry by lambda. So lambda times I is going to be lambda 0 to 0 lambda. I'm just telling you that's what you do when you multiply a scalar times a matrix. Likewise, you can subtract matrices in the seemingly obvious way. Subtract entry by entry. Take the upper left entry for A, subtract the upper left entry for lambda I to get the upper left entry for A minus lambda I. So that will be 1 minus lambda. Take the upper right entry, 3, subtract the upper right entry of this one, 0, to get the upper right entry for A minus lambda I, just 3. For the lower left entry, you'll do 2 minus 0, which is 2. And for the lower right entry, you will do 2 minus lambda, and get a 2 minus lambda. I'm setting this equal to 0. I'm trying to solve for the values of lambda that will make that true. So take the determinant now. Do the product of the quantities in the upper left to lower right, main diagonal it's called. 1 minus lambda times 2 minus lambda. Subtract the product of the numbers on the off diagonal. 2 times 3 is 6. That's a quadratic equation in lambda. I should simplify it into standard form. Factor it if I can. If I can't factor it, I try to use the quadratic formula. Let's see. FOIL that out. You'll get a positive lambda squared. Negative lambda times negative lambda. Minus 3 lambda plus 2 minus 6 equals 0. Don't forget the minus 6. It's a common mistake to forget that. So what do we have here? Lambda squared minus 3 lambda minus 4 equals 0. We don't need the quadratic formula. That one's pretty easy to factor. Lambda minus 4 times lambda plus 1. So your solutions are negative 1 and 4. Those numbers are called the eigenvalues of A. The word eigenvalues is kind of a cross between a German and an English word. Eigen, I think, means maybe something like characteristic or something. Characteristic value. Eigenvalue, kind of a cool name. Those are the eigenvalues of the matrix A. And the significance of these is these are now going to correspond to values of lambda where there will be non-zero solutions for V in this equation, as well as that equation because they're equivalent. So now I have to find the corresponding vectors. They're called eigenvectors. Find the corresponding eigenvectors. I will typically shorten it to E vectors and E values, but you should never forget that E stands for eigen here. And when you find both eigenvalues and eigenvectors, I like calling that finding eigenstuff. Okay, that's just my terminology. Find the eigenstuff. Consider each eigenvalue separately. Let's consider negative 1. Plug negative 1 in for lambda here to solve that for non-zero V's, or equivalently plug it in here. And this one's typically the quicker way to go. Plugging it in here. Which means, remember, this is the matrix A minus lambda I. Focus on that matrix, ignore the determinant now. Replace the lambda with negative 1. you're going to get 1 minus negative 1, 3, 2, 2 minus negative 1. You're solving for v, whose components are x and y, to make this 0. Focused on that form of the equation. I could have done it with this form, but it's quicker to do it the other way. That's a 2, this is a 3. Hey, these columns are multiples of each other. They're not linearly independent, they are linearly dependent, and that is enough to know that there's going to be non-zero solutions. And in fact, we can just consider the corresponding scalar equation that corresponds to one of the rows. They're the same equation, in fact. 2x plus 3y equals 0. In fact, you can skip writing it as terms of a matrix. You can just jump when you get enough experience, you can just jump right to there. You still need to think about this thing. But effectively, if you're confident you've calculated the eigenvalues correctly, you can just focus on one or the other row. This time the equations are the same. In general, they'll be multiples of each other. What does this say? This has infinitely many solutions. You can solve it for y in terms of x like this. And what you typically do now is you pick some value of x, some non-zero value of x, and use this equation to determine y. What would be nice to pick for x here? How about 3? Because if you pick x to be 3, then y will be negative 2. They'll both be integers. This is a little tricky. You gotta be careful. Sometimes this makes people think that x and y have the same sign if you get both positive coefficients. But no, in that case, they have opposite signs. I can pick anything for x as long as I don't pick 0. I don't want to pick x equals 0 because I don't want to think about, I want non-zero solutions. So that's an eigenvector corresponding to this eigenvalue. It's not unique. Any non-zero multiple of this will also be an eigenvector corresponding to that eigenvalue. We're running out of time. Try to wrap it up here quick. Without fully explaining things, next find the eigenvectors, or at least one eigenvector corresponding to the other eigenvalue, 4. Do the same kind of thing. I'm just going to focus on the top row of this matrix. Replace lambda with 4. 1 minus 4 is negative 3. I would get negative 3x plus 3y equals 0 if I focus on the equation that comes from the top row. If you focused instead on the equation coming from the bottom row, you'd get 2x minus 2y. If lambda is 4, 2 minus 4 is negative 2. 2x minus 2y is 0. It's an equivalent equation. Both of those equations can be thought of as y equaling x. Is the simplest form of it. And that means the corresponding eigenvector you can take to be 1, 1, or any non-zero multiple of that. The punchline now is that the general solution of the original system can be written as a general linear combination of e to the lambda t times the corresponding eigenvector. E has got to come in there somewhere, the number e. The general solution, y, which is a function of t, k1 e to the negative t corresponding to lambda equals negative 1 times the eigenvector corresponding to lambda equals negative 1, 3 negative 2, plus k2 e to the 4t. 4 is the other eigenvalue, and a corresponding eigenvector is 1, 1. That's one form of the general solution, where k1 and k2 are arbitrary. If I picked non-zero scalar multiples of that and non-zero scalar multiple of that, I get another form of the general solution. There are infinitely many ways of writing the general solution. When you solve initial value problems, you've got to solve for k1 and k2. which typically involves a system of equations, linear equations to solve for K1 and K2. And you'll get a unique answer no matter how you decide to write your general solution, as long as it's a correct form of the general solution. I'm using the linearity principle here without saying it until now. You can check individually that this function and this function solve the original system, the original differential equation. You can check it directly by substitution. And essentially the linearity principle says, when you've got a linear system like this, that a linear combination of two solutions is another solution. And moreover, if those solutions are linearly independent, which means they're not scalar multiples of each other in a two-dimensional situation, that this is the full general solution. Every solution can be written like this for some K1 and some K2. It's all motivated by the idea of finding straight line solutions. And you'll see that in the reading if you haven't done the reading yet, by looking at the vector field to help us guess that an equation like this might have some non-zero v's that solve it for some lambdas. Any questions at all? All right, let's end it there. Have a great spring break. We'll see you in, 10 days? We will have class that Monday. See you then.